So in example 2, we are going to look at a general ring, and we're going to use a subring test to prove that the set C that's defined here is a subring of R. So we're not looking at any specific ring. We're not looking at like the integers or the reals or some kind of ring of matrices. We're going to look at just a general ring R, and then C, our set C, is defined to be all the elements in our ring that commute with everything else in R. So that's like the equivalent of what we called a center for a group before, when we had, especially interesting to look at when we had a non-commutative group. And since our ring doesn't have to be commutative under multiplication, this might be an interesting set to look at, to actually look at all the elements in our ring that commutes with everything in the ring. It was a subgroup. The center is a subgroup of a group, and so here we're getting a similar result for a subring of a general ring R. Okay, so we're going to use our subring test, and so there are 3 things that we need to show are true about our set C. The first one is that C is non-empty. Okay, so is it non-empty? And to show that it's not empty, well, it would be good to find something that's in it. And I'm claiming that 0, our additive identity, is in our set C. And let's see why that is true. Well, certainly, since R is a ring, zero is in R, and A times 0 is equal to 0 is equal to 0 times A, and that is true for all, no, I squeeze it in here, for all A and R. We saw that in our rules of multiplication. But that is exactly the definition of what puts something inside of our set C. And so thus we have that 0 is an element in C, and so C is non-empty. Okay, first one done. Second one has 2 pieces. Closure under, well, let's call it subtraction. It's not really, and multiplication. But so what we mean by that is for all R and S, let's say, in C, we have that R minus S is in C and R times S is in C. So those are the 2 things that we need to show. All right, so let's do it. So take any R and S and C, and then let's look at what A times R minus S looks like. Because we want to show that A times R minus S is equal to R minus S times A, so that we can conclude that R minus S is an element in C. Because that's a condition. Does it commute with A or not? So let's see, A times R minus S, we have distributivity, so that is A times R minus A times S. But that is equal to R times A minus S times A. And why is that true? Our ring is not commutative, but C picked out exactly the elements in R that commutes with everything, and R and S were supposed to be in C, and so they do commute with A. So that's our reason. So this is true because R and S are elements in C. Okay, but then now we can just use distributivity again, the other way around. So this is R minus S, and then we have A multiplied on the right side. And that is exactly our condition that shows that an element is in C, that A times that element is equal to that element times A. So we have that R minus S is an element in C. So that was the first piece of number 2, and then the second piece of number 2. Let's look at R times S. What is true about R times S? Does that commute with A or not? All right, so A times R times S. How can we get that A on the other side? Well, first we need to multiply it in a different order. And we can do that because we have associativity. So we have that. But R is an element in C, and so R commutes with A. So I can flip R and A and then multiply by S. So that is true because R is an element in C. Okay, and now we're basically doing those two steps again. We have associativity. So now we can look at R times A times S. And S is also an element in C. So we have R, this is equal to R times S times A. So that is, since S, gotta fix that. Since S is an element in C, but now we can use associativity one last time to have our result written exactly the way that we wanted it. So we have A times R times S is equal to R times S times A. So R times S commutes with A, and that means that R times S is an element in C. So we did it. Last sentence. By the subring test, C is a subring of R.